All right, today we are looking at polygons, but we're specifically looking at polygons inside of a coordinate plane. And we're going to do what's called a coordinate proof with that. So I'm going to kind of do an abridged version of it, but it kind of gives you the picture of what's going on with it. So our objective today is that we want to prove and verify a polygon through the use of algebra in a coordinate plane. That's kind of the big thing that we're going to be doing here. And so what a coordinate proof is it's just a specific kind of proof that you're going to use that coordinate plane and you're going to use your algebraic steps to be able to show that something is going to be true. So I've got two examples here that we're going to take a look at. So this first one here is prove that this polygon is a triangle. So the real thing that we've got going on here to prove that it's a triangle is that your two small sides have to be greater than your third side there. So if I picked any two of these sides here, then if I add those together, it needs to be bigger than that bigger side. And so that's kind of how you can prove that it's going to be there. I'm going to take it one step further and prove what type of triangle this is. And so that's kind of what we're going to do. And so the first thing that we want to do is we want to choose what our needed points are. So let's go ahead and we're going to take a look at DE. So that's going to be the first thing that we're going to look at. And so what we're going to do is we're going to choose our points. So I'm going to do E is 3, 3, and then D is negative 3, 3. So I'm going to choose those points, and now I'm just going to label them and put them into my distance formula. So that's my first x, and this is my second x, this is my first y, and this is my second y. And so it doesn't matter what order as long as these numbers are the same in each of those points, and that you have your x's first and your y's second in those points. And so once I do that, I'm going to take that, I'm going to put it straight into my distance formula. So it's really intimidating formula, but it's not that difficult to use. So I get negative 3 is 2, or x2, and then x1 is positive 3. So x2 minus x1 squared plus, and then we've got y2 is 3 minus y1 is 3. And so 3 minus 3 just comes out to be 0. And then this, negative 3 minus 3 is negative 6. And so that's kind of what that looks like when we start simplifying it. Well, negative 6 squared is just going to be 36, and 36 plus 0 is just 36. So that means we get square root of 36. So the distance of this, if I plug that into my calculator, or if you know, it's just going to be 6. So I know that this length right here is 6. I could technically have just kind of looked at it and said, hey, I know that I'm going to have 6 points there on this coordinate grid. But again, we're trying to prove, and just sitting there and counting on there isn't going to necessarily prove it for me. So the last thing we want to do is we want to repeat that for each side. And so like if I do EF next, so I've got this side here that I'm doing next, I'm going to do 3, 3. That's my first point, and then 0, negative 3 is my second. So I'm going to label my points. Oops, that's y2. And now I'm going to plug my numbers in. So 0 minus 3 squared plus y2 is negative 3 minus y1 is 3. So 0 minus 3 is just negative 3 squared, which just comes out to be 9. And then negative 3 minus 3 is negative 6. Well, negative 6 squared is 36. And so I get 9 plus 36. So that comes out to be the square root of 45. And we plug that into our calculator, it comes out to be about 8.7. So I get that this side is 8.7 right here. And this side over here, in the interest of time, I'm not going to actually go through and do that, but you can see it's going to come out to be the exact same thing here. So like I could go through and I could plug it into here. I know that that's going to end up being a triangle, but since I've got two congruent sides, I can say that this is an isosceles. I think that that's spelled right. Don't quote me on that, but isosceles triangle. So that's kind of what you're going to be doing, and you're just using the distance formula to do that. So let's jump over here. So on this, we know that AT is parallel to MH. We need to prove that this polygon is a parallelogram. Well, if we're going to prove it, then we're going to plug this into the distance formula. And so I'm going to kind of do an abbreviated version of this just because I'm running out of time here. But you can see, label your points. So I've got X1, Y1, X2, y2, plug them in, I get 6 squared, or 6. So this side is 6 and this side is 6. And since I have that there, one set of parallel and congruent sides is enough to prove that it's a polygon.